Okay, in this video I want to do an example of proving that a subset of Rn is a subspace for some examples. So here's a typical example. Prove that the set W, which is the set of x1, x2, x3, such that x2 equals x1 plus x3, is a subspace of R3. So let's just be clear what this notation means. Right? When I see that W is equal to vectors of this form, then, satisfying this equation, I see that W is a subset of R3. So I already see that W is a subset of R3 because I have three components here. And this means, this colon means with a property that, or such that, x2 equals x1 plus x3. So what that means is that the second component, x2, is equal to the sum of the first component and the third component. So if you have a vector in R3 such that the second component is equal to the sum of the first and third component, then it's in W by definition, and otherwise it's not in W. And we want to show that the set W is a subspace of R3. Okay. Well, different books have different but equivalent axioms for what makes something a subspace, but by definition, a subspace of R3 is a subset of R3 that's non-empty and that's closed under addition and scalar multiplication. So the first thing we need is to show that the set is non-empty, that W is non-empty. It turns out that if you have a subspace and if your set is non-empty, then it must contain the zero vector. So some books will phrase the first thing to check is that W contains the zero vector. And let's just do that. If it contains the zero vector, then of course it's a non-empty set. So how do we check that the zero vector is in here? Well, remember, what do we need to do to check whether something is in W? We need to check whether the second component is equal to the first component plus the third component. That's what this condition for W means, right? If you think about what makes something in W, it's whether this equation holds. So let's say that you have the zero vector. Well, if our vector x1, x2, x3 is the zero vector, then x1 is 0, x2 is 0, and x3 is 0, right? The first component is 0, the second component is 0, and the third component is 0. And so, we need to check whether the thing on the left, x2, is equal to the thing on the right, that's x1 plus x3, and we can just do that out, right? x2 is just 0, and x1 plus x3 is, x1 is 0 in the case of the zero vector, and in the case of the zero vector, x3 is 0. So x1 plus x3 is 0 plus 0, which is equal to 0. And so we found x2, it's 0. We found x1 plus x3 is also 0. So since x2 is 0 and x1 plus x3 is 0, they're the same. We have x2 equals x1 plus x3, which implies that this vector, 0, 0, 0, is in fact in the set W. So that shows that the zero vector in R3, which is 0, 0, 0, is an element of W. Okay, the next thing is closure under vector addition. So recall what that means it means that whenever you have two vectors in W and you add them, the result, the sum, is also an element of W, this set W. So what do we need to do? We need to start off with two random vectors in W, right? Arbitrary is the technical term, and add them and somehow check that the result is an element of W. And the difficulty is that since W has an infinite number of vectors, it's impossible to work with specific numbers. We have to just work with two vectors in W and somehow use the fact that they're in W to show that the sum is in W. So how that works is this. So the first sentence, and I'm assuming that if you're watching this, you're new to writing proofs, but the first sentence should be, let A be in W, A be an element of W, and let B be an element of W. Of course, they don't have to be A and B. They could be U and V, X and Y, V and W, V1 and V2, anything. The point is that you need to start off with two elements of W. And we want to show that the sum, A plus B, is an element of W. So let's just do some scratch work. Since it's scratch work, I'll do it in a different color just to make it clear. So this wouldn't be part of the final proof, but it gives you an idea of how we're going to do this. So what we're given is two vectors in W. So, we're given that A is an element of W, and we are given that B is an element of W, where W is defined by this equation, x2 equals x1 plus x3. And what we want to show, let's just put the destination here. What we're trying to conclude is that the sum A plus B is an element of W. So the question is, how do we get from what we're given to where we're trying to go, right? In our proof, this is going to be the last sentence. The last sentence of the proof is going to say, so A plus B is in W, or therefore A plus B is an element of W. The question is, what goes in between? We have to somehow use what we're given and somehow arrive at this conclusion. Well, since W is defined in terms of coordinates, right? W is defined in terms of what happens to the components of the vectors. If the second component is equal to the first and third components added together. So what we should do is we should work with the components of A and B. And so we should say, suppose that that A has components A1, A2, and A3, and B has components B1, B2, and B3. What this sentence is doing is we're just introducing the notation for the components of the vectors. And what do we want to show about these numbers, A1, A2, A3, and B1, B2, and B3? Well, what does it mean for A plus B, this vector, A plus B, to be an element of W? What does it mean for a vector to be in W? It means that the second component is the sum of the first and third components. Well, what are the components of A plus B? Well, that's easy. We just add them, right? So suppose that A is A1, A2, A3, and B is B1, B2, B3. Then A plus B is equal to, by definition of vector addition, A1 plus B1 A2 plus B2, A3 plus B3. So the first component is A1 plus B1, the second component is A2 plus B2, and the third component is A3 plus B3. And what it means for a vector to be in W, for A plus B to be in W, is that this second component is equal to the sum of the first and third components. So what we want to show is that the second component, A2 plus B2, is equal to the sum of the first component, which is A1 plus B1, and the third component, which is A3 plus B3. So if we can show that this equation is true, then we're done, because that's what we need to show in order to prove that A plus B is in W. Well, we know that A is in W and B is in W, and we need to work with that, right? A isn't just any random vector in R3, it's a vector in W, so we need to use that fact somehow. Well, what does it mean for A to be in W? Since A is in W, what that means is, by definition of W, let's just recall, here's the definition. The second component is the sum of the first and third components. So since A is in W, we have the second component, A2, is the sum of the first component and the third component. And similarly, since B is in W, we have that the second component, B2, is the sum of the first and third components. So really what we know about the components of A and B is these two equations. These are the equations we have to work with, and we're trying to get this. Well, do you see how, I mean, you know, these are real numbers we're talking about, right? I mean, A1, A2, A3, B1, B2, and B3, these are all real numbers. And so we're trying to show that if you know these two equations, you get this single equation. So what can we do? We can just add them, right? I mean, if I have these two equations, I have A2 here, I have B2 there. If I add them, I'm going to get A2 plus B2 on the left. So if I add them, I get A2 plus B2 is A1 plus A3, that's A2, and plus B1 plus B3, because that's B2. So I know that this equation is true. Can I deduce that this equation is true? Well, yes, because I have properties of real numbers, right? When you have real numbers, you can switch the order in which you add them. And if I switch the order in which I add them, I'm going to get A1 plus B1 plus A3 plus B3. By switching these two and using the associativity of addition, right? And that's essentially the proof. So actually, our proof, I'm going to write it all out just to make it very clear. But let's move this down below. Going back to what we actually write down, now that we see the proof, we want to show that A plus B is in W. Well, actually, we end up pretty much just writing what we had before. So suppose that A is A1, A2, A3, and B has components B1, B2, and B3. Then we know that A plus B is A1 plus B1, A2 plus B2, A3 plus B3. And since A is in W, we have A2 is A1 plus A3. And since B is in W, we have B2 is B1 plus B3. So therefore, what are we trying to show? We're trying to say something about A2 plus B2, right? So therefore, A2 plus B2, given these two equations, it's equal to A1 plus A3 plus B1 plus B3. And this is equal to, by properties of real numbers, A1 plus B1 plus A3 plus B3. And that shows that the sum, A plus B, is an element of W, because I've written the second component as the sum of the first and third components of A plus B. So this is the proof. Okay. This proves that the set is closed under vector addition, and just to be clear, even we could even say therefore W is closed under vector addition. So to me, this is like a model proof. This is like as perfect a proof of vector of closure under vector addition as it can get. Okay, so you start off with two elements of W, and you add them and show, using the properties of W, that the sum is in W, and then you conclude that W is closed under vector addition. It takes a while to get used to this if you're new to proofs, but once you're familiar with proofs, it's easy. Okay, so the last thing is closure under scalar multiplication. And what that means is whenever you have a vector in W and a real number, C, the scalar multiple of that vector by C is also an element of W. So what we need to do is we need to start off with a vector in W. So let's just call it V maybe. Well, we don't have to. Let's just call it A, because our components of V will be V1, V2, and V3, and sometimes that's used for vectors. So let's just let A be in W and let C be a real number. So what we want to show is that C times A, this scalar multiple of A, is an element of W. Okay. And so we're given that A is in W, so suppose that A has components A1, A2, A3, and I write that by saying that suppose that A is A1, A2, A3. So since, let's just write down what it means for A to be in W, A2 is A1 plus A3. And again, we can just do scratch work just to explain how our proof is going to go. So what we're given is that A is in W, and we're given that C is in R. And our destination is we want to show that the scalar multiple CA is an element of W. And what we have to work with is the coordinates, the components of A, which is, so suppose that A is the vector A1, A2, and A3. Now we can actually work with these real numbers, A1, A2, and A3. And what do we want to show? Well, we know we want to say something about CA, right? We want to show that it's in W. So what's the vector CA? Then CA is the vector CA1, CA2, CA3 by definition, right? You multiply each of the components by C. And recall again, just in case you don't remember, that W consists of the set of vectors with the property that the second component is equal to the first component plus the third component. So don't get, thrown off by the letters and the symbols. I mean, this, what the names of these components are isn't important. It's just saying that the second component is the sum of the first component and the third component. That's how you want to interpret what this set is saying. Okay. So for CA, going back to that, what's the second component? It's CA2. So we want to show that CA2, the second component, is the sum of the first component, which is CA1, and the third component, which is CA3. So we want to show that C times A2 is C times A1 plus C times A3. And if we can do that, then that proves that CA is an element of W. Well, what we know is since the vector A is in W, what does that tell us? That tells us that the second component of A, which is A2, is the sum of the first component of A, which is A1, and the third component of A, which is A3. And now do you see how we can work with this equation? This is the equation we have to work with. How can we go from here to here? Yes, we can multiply both sides of this equation by C, and that will give you a C times A2 on the left, and then it'll give you C times parentheses A1 plus A3 on the right, and then when you distribute, you're going to get that. Okay, perfect. So let's write that down. So since A is in W, we have A2 equals A1 plus A3. So C times A2 is going to equal C times parentheses A1 plus A3, and that, by the distributive property, is C times A1 plus C times A3. And that's what we wanted to show, right? We showed that C times A2 is, when you have something that's equal to something and that's equal to something else, that amounts to saying that the first thing is equal to the last thing, right? So C times A2 is CA1 plus CA3, which is what we wanted to show. Which is what we wanted to show. So now we're ready to write our proof. Let's move this down. The proof is going to go, so suppose that A is A1, A2, A3. Since A is in W, A2 equals A1 plus A3. So C times A2 is equal to C times parentheses A1 plus A3, which when you distribute is CA1 plus CA3. And since I showed that, that the second component of CA1 is the sum of the first and third components, we're done. So CA2 is CA1 plus CA3. Therefore, C times A is in W. If you wanted to write out a bit more detail, we could include a sentence here that says, then CA is CA1, CA2, CA3, and we want to show that CA2 is equal to CA1 plus CA3. That might make the explanation a bit clearer. So the proof will go, I mean, I don't think it's super necessary, but it's probably a good idea if you're new to proofs to include this. So let me move this down. Okay. Let's see. So to write out all the details, we would suppose that A is A1, A2, A3, then CA is CA1, CA2, CA3. We want to show that CA2 is CA1 plus CA3. And then we would say, since A is in W, we have A2 is A1 plus A3. So CA2 is C times A1 plus A3 equals CA1 plus A3, therefore CA is in W. And so therefore W is closed under scalar multiplication. And so we've shown all three things. We've shown that W contains the zero vector. That's what we concluded here. We show closure under vector addition, right? Our last sentence was therefore closed as W is closed under vector addition. And then we showed that W is closed under scalar multiplication. And so when you put 1, 2, and 3 together, we conclude that therefore W is in fact a subspace of R3. Okay, let's see. So that would be the entire proof. We can move maybe the scratch work. Well, I don't know. Farther. Oh dear. Oh no, we should not have done that. Well, anyway, so this would be the entire proof. It's 1, 2, and 3 before I accidentally did that. Okay, so usually a lot of people, because it takes time to do this, usually I've seen videos of showing that something is a subspace, but they save time and they sort of cut corners. But if you really want a complete proof, I think it's a good idea to see what it looks like, and what I wrote down is a complete proof. And then we can talk about, okay, can you make the proof shorter? Can you make it less written out in complete detail? Yes, there are ways to do that, but I think that for starting out, showing that something is a subspace, you want to see what a complete proof with all the details looks like first, and then once you understand that, then we can discuss, okay, can we cut down some of the sentences and make it a bit shorter while still showing all the important steps. Okay? So that's an example of how to show something as a subspace. It does take time, but in this video, we really did go over every single step that you need, and we explained why we did the steps we did. Okay, thanks for watching.